Hello students, in this video we'll solve a competition problem that involves proving that there exists an isosceles tetrahedron. Here's the setup of the problem. Let's let A, B, and C be the side lengths of an acute triangle. Prove that there is a tetrahedron, A, B, C, D, with A what? With AB equals CD equals C, with AC equals BD equals B, and AD equals BC equals A. Okay? Great. So how do we do this? How do I prove that such a tetrahedron exists, right? Well, note, the law of cosines tells us, since remember that we're in an acute triangle, okay? So that means that alpha, beta, and gamma in that triangle are all between 0 and 90, and the cosine of a number between 0 and 90 is going to be positive, right? It's an acute triangle. So by the law of cosines, I have a squared plus b squared minus 2ab cosine gamma is c squared. But this is a negative number over here. So that says that a squared, so that number is negative. So I throw it on the other side, it's positive, right? So that says that a squared plus b squared minus c squared is greater than 0. And I can cycle these, right? So I get three things from this. I get a squared plus c squared minus b squared is greater than 0. And I get b squared plus c squared minus a squared is greater than 0. That just comes from the fact that it's an acute triangle, right? That's nothing more than just the law of cosines. Now what we can do is these are positive numbers, so I can find their squares of some other numbers. So I'm going to let r squared be a squared plus b squared minus c squared over 2. S squared is equal to what? Let's see, I want s squared to be a squared plus c squared minus b squared over 2, and then finally t squared is going to be equal to what? Is going to be equal to b squared plus c squared minus a squared over 2. Okay? That comes from the fact these numbers are all what? They're all positive, right? And so positive numbers are the squares of something, right? Great. Now what we're going to do is we're going to build a cube, right? So build the cube, build a box rather, cube, plus minus r over 2 plus minus s over 2 and plus minus t over 2. So we have a cube, alrighty, or box rather. And what I'm going to do is I'm going to connect vertices in this box, right? So what I'm going to do is I'm going to set A, let's build the tetrahedron now. Let's define A to be equal to what? To be equal to r over 2, s over 2, t over 2. Then I'm going to let B be r over 2, and then negative s over 2, negative t over 2. We're going to let C be what? Negative r over 2, and then s over 2, and then t over 2, like that. And then finally D, and then this one's negative 2. And then finally D is going to be what? Then D is going to be, and finally D, which is going to be what? The first two are negative. Negative r over 2, negative s over 2, t over 2, okay? All right, and so now, this is going to be a what? So then, now, A, B, C, D is a tetrahedron. Beautiful, okay? So I have a rectangular box, right? Rectangular prism, and I have a tetrahedron inside this rectangular prism. Okay, that's the idea. So we want to think of this, it's a box, so it's a rectangular box actually because it's parallel, right? So I have a rectangular box, okay? Of course, I'm thinking of a special case of a cube when it's equilateral one. That's what I'm thinking of in the back of my mind, right? But it works in general in this case. Now I need to prove these relationships over here, right? And so let's do it. So how do I compute AB, for example? What's the distance between AB? AB is going to be the square root. What's going to happen over here? The r is going to cancel out. I'm going to have an s squared plus t squared, right? So it's going to be s squared plus t squared. And what's s squared plus t squared? S squared plus t squared is just going to be c squared, right? So this is going to be the square root of c squared, which is just going to be c. What is CD? CD over here is going to be the square root of what? CD, so here's C and here's D. The R's are going to cancel. I'm going to have an S over 2 and then a T over 2. So it's going to be S squared plus T squared. That's going to be square root of C squared. That's going to be C. We've just proven that A, B equals CD equals C. Good. Let's make sure the other ones work out in the right way. What's the next one? I need to look at AC. What's AC going to be? So AC is going to be the square root of what? AC, let's see what's going to cancel on AC. What's going to cancel on AC? I get R squared. That square cancels. I get an R squared plus T squared. What's R squared plus T squared? R squared plus T squared. What's going to cancel? The A's cancel. The C's cancel. It's going to be B squared. Square root of B, which is just B. And what's BD? BD is the square root of what? Let's see. So there's B and there's D. It's going to be R squared. That squares cancel out R squared plus T squared. Oh, look, that's beautiful. R squared plus T squared. Square root of B squared, which is B. So we've just proven that AC equals BD equals B. Cool, that works. And finally, what's the last one? Hopefully this works out completely correctly. We made all the right sign choices. The next one's going to be what? The next one's going to be AD. What's AD going to be? So AD is going to be the square root of what? Let's see, so here's the A and here's D. I get an R squared, I get an S squared, but no T squared. I get R squared plus S squared, which is what we want, R squared plus S squared. What's R squared plus S squared? R squared plus S squared, the C's cancel out, and the B's cancel out, just gives me an A squared, which is A. And finally, what's the last one? BC is going to be the square root of what? BC is going to be R squared, S squared, no T squared. R squared, S squared, no T squared, that's square root A squared. That's A. Therefore, AD equals BC equals A. And we got it. And these are special, of course, tetrahedron, right? They're called isosceles tetrahedron, essentially, right? Because the faces all have these properties over here. There's a fact that two of the sides are going to be two of those sides are the same, right? So we call this an isosceles version of a tetrahedron. Thank you very much.